Hello everyone. Today's lecture will be on feature extraction. Our main goal is to look at an image like this and extract descriptors or features that will represent the image. Keep in mind applications such as tracking of objects in a long video, determining correspondences between two different scenes, or simply recognizing objects, seeing that in this image there are multiple cars, we're in a road, there are buildings, and so on. And feature extraction is an essential component in this framework. When we talk about feature extraction and afterwards the matching, the idea is a feature is a description of a part of a pattern or object in the image, such as shape, texture, emitted heat if infrared. Mathematically, this basically means that we describe the pattern with a vector of values. For example, a feature can be this f equals to f1 to n, where it describes that we have n features. Now, we can discuss whether we extract features locally, meaning that we extract features in small patches in an image, such as this, and obviously in that case, we will have many different patches, and we would have descriptors for each of these patches. Or we can actually talk about extracting features from the entire image, just one big vector that describes the entire image. Now, the goal of feature extraction, as we talked about, is registration, correspondences, tracking, and recognition. And the two problems that you should keep in mind, I think, which describes the inherent challenges in this problem quite well, are the specific object recognition and object category recognition. The problem with specific object recognition is identifying the same object in multiple scenes. It's actually quite useful in tracking objects in videos, finding correspondences between different scenes for registration, and multiple applications research in industry are done by specific object recognition. The problem can be actually shown nicely with these images. Here at the top, we have two objects, and at the bottom, we have these objects in their natural scenes. And the idea is specific object recognition would be to recognize these objects, even under these clutter and changes. Just as they can be under clutter and changes, you can actually observe that you have very different viewpoints and very different deformations of the same object. The second problem is the object category recognition. Here, the idea is to recognize different instances of the same object. For example, in the scene we talked about already, it will be identifying all the cars. They all have similar patterns, but they all have variations as well. So in addition to the challenges in specific object recognition, now the intrinsic variation within the category also plays a crucial role and creates or poses a challenge for recognition systems. So the challenges in recognition, or as we discussed today in feature extraction, are differences in viewpoints. We can have the same object viewed in different viewpoints, and we want to be able to extract features that are useful to recognize this object even in this variation. Variations in illumination will happen. You can have the same scene under different lighting conditions. If you think about autonomous driving applications, that would be really having the same scene under sunny days, under foggy days, under night even. The background changes, so you will have to be able to detect or create features that's useful to detect objects, even when what's behind the object changes. Objects may be cluttered, so they are occluded by different structures. For example, here the task is occluded by this bottle. We want to be able to recognize objects even though some part of it is not visible. And lastly, when all these four challenges are are inherent in specific object recognition, as well as object category recognition. On top of this, when we talk about object category recognition, we talk about intra-class variation of the appearance of the object. We can have different koalas in different forms, in different viewpoints, in different lighting conditions, as well as in different colors and inherent changes, that's the variations that inherent to the species. We want to be able to create features or have methodologies to extract features from these images that are useful to recognize these objects or match these objects, despite all these challenges. The considerations we have when selecting features are fourfold. First, we want to choose features that are either complete or not. Complete meaning a feature that describes the pattern unambiguously. So really, there is a just unique feature for a single pattern. We want features that are robust in extraction, as well as it's easy and it's fast to extract them so that we can use them in real applications. And the last choice that we have is whether to extract features that are global, meaning they represent the entire image with one vector, or local, meaning we extract features from various patches in the image. So we would have multiple features describing different areas in the image. When we talk about robust systems that can withhold all these challenges that we talked about, we're actually looking at non-complete representations and local representations. And to this end, to make it a bit more concrete, we will have a strategy that's in two parts for extracting features that can actually be useful to do all the tasks we talk about despite the challenges. The first part will be identifying points of interest. What this means is if you look at these images, there are certain parts that are actually indicated by either rectangles or ellipses. These are points of interest that an algorithm finds in an image. They're distinct points. The second part is to extract local features, so meaning vectors of numbers, around each of these interest points. That means once you have an interest point, find a patch around it and represent the intensity variation or the intensity in that patch with a small vector. We will extract many features per image. And our hope is that different features will represent different parts of many objects. So when we do matching, we can actually do local matching. We can have different clutter, different number of objects, different backgrounds in the image. These local feature matching or local feature extraction can actually extract similar features despite all these variations in the images. The first part will start with identifying basic points of interest. So what does it mean to be a point of interest, and how do we actually extract them computationally? An interest point basically means a localizable patch in an image. So a feature that we want to extract should capture something discriminative about a well-localizable patch of a pattern. And we will at this point start with the well-localizable bit and talk about the interest points. So a patch should be distinct with respect to its surrounding. In this case, for example, this patch in the ear, you can see that actually it's distinct from all its surrounding where you have homogeneous tissue or you have different structures here. Shifting the patch a little bit to any of the directions should make a big difference in terms of the underlying pattern. And moreover, we should be able to get the same point of interest under pose and lighting variations as much as possible. I think for visually, one can find out such patches quite easily, the interest points. Now we will talk about three different approaches to have computational algorithms that identify such points of interest. We will talk about edge detection, specifically three different types of edge detections based on gradient operators, zero crossings of Laplacians, and Kenny edge detector. And then we will talk about corner detection and blob detection. The underlying idea in all these approaches is the fact that if I look at an image like this, it's really the edges and the corners that are quite distinct and give the context in the image. Of course, all the texture and all the different gray level intensities are important as well to make the distinction, but to basically say something is a car or a road, I really rely on these corners, on these edges, and how they're combined together. Moreover, notice that the edges and the corners, they remain visible even after viewpoint and illumination changes. So they are actually quite robust to some changes. Let's start our discussion with the edge detection. Now, the edges arise from various changes in reflectance, orientation, illumination. So actually, not all edges are necessarily relevant to an object. The ones that are relevant to an object are really at the boundaries that can actually be created due to the reflectance properties of the different objects, the background and the foreground. The methods we introduce here form only the first step, basically really identifying points that might be edges. But combining them to extract, for instance, boundaries of an object is a much harder question that we will talk a little bit about in the segmentation lecture. Now, the edge detection methods really have three distinct approaches. One of them, the simplest one, is simply identifying the highest intensity gradient magnitudes. So if I have an edge like this, a profile, and if I look at the gradient of this profile, I should be getting something like this. Notice that the highest point at the gradient profile also corresponds to the center of the edge or center of the edge profile here. The second one is locating inflection points in the intensity profile. If I have the edge profile like this, you can imagine that, well, the first derivative achieves maximum at the edge, so the second derivative should achieve a zero at the edge. The second derivative, or the inflection point, should be able to detect it by just looking at the zero crossings of the second derivative operator. So that's another way of finding edges. And the last one is the signal processing view, so creating an optimal detector for edges. In the first two, we described this profile, which is quite ideal. There is no noise here. In reality, we actually observe a profile like this, and we want to be able to extract edges even in the presence of such high noise. Before we talk about or start our discussion with the first edge detection method, I'm going to stop the video here and upload it so that they're in small chunks.